In this lesson, we will learn one of the most interesting circuits made with op-amps, the integrator. Integrators can be used to simulate differential equations using electric circuits. In previous lessons, we have briefly seen the behavior of integrators. An integrator is a device that accumulates a quantity. A capacitor accumulates current, a bucket accumulates water. In the diagram, we can see an integrator block which will accumulate the value of the input signal. The input is a pulse wave that has both positive and negative values. But the time the pulse spends on the positive value is larger than the time it spends on the negative. In the simulation, we can see in blue the input. The output of the integrator is shown in orange. We can see that when the input is positive, the integrator output increases. When the input is negative, the integrator output decreases. On average, we can see that the integrator output keeps increasing. That's because the input spends more time on the positive side. Therefore, the accumulated value over time is positive. An integrator is described by the following differential equation. The variable y represents the output, while the variable x is the input. There is also the term k, which is the gain of the integrator. If you remember, in the previous lesson when we talked about capacitors, we mentioned that a derivative represents a rate of change. In this case, the time derivative of y is the rate of change at which the output will change. In this case, when the product k times x is positive, the output will increase. The larger the value, the faster will increase. Previously, we learned the equation of the current of the capacitor. If we rearrange the equation, we can make it look like the integrator equation. We can see that the capacitor accumulates current, and that is reflected as the voltage value. The gain of the integrator is given by 1 over C. Therefore, the larger the capacitor, the slower the voltage will increase. When processing signals, it is usually easier to work with voltages. The circuit we will see is an integrator that takes as input a voltage and outputs a voltage. In this diagram, we can see the circuit. This looks like an inverting amplifier, but it has a capacitor in the feedback path. We could analyze it using the Laplace transform, but the circuit is simple. We will work with the differential equations. We can simplify the analysis using the virtual ground concept. With that, we have two currents flowing into the inverting pin. The current of the resistor IR1 and the current of the capacitor IC1. There is no current into the op-amp. The current IR1 is equal to the input voltage over the resistor R1. The current of the capacitor is given by the differential equation. The voltage of the capacitor is the same as the output voltage. Therefore, we write the term Vout in the derivative. After rearranging the equation, we can see how this circuit is an integrator. The gain of the integrator is minus 1 over R1 C1. Here we can see a simulation using the circuit. The input voltage is a symmetric pulse. The value of the resistor is 10 kilo ohms and the capacitor is 10 microfarads. With those values, the gain of the integrator is minus 1 volt per second. That means that given an input of 1 volt, it will take the output 1 second to reach a level of minus 1 volt. In the simulation, we can corroborate the result. When the input is positive, the output of the integrator decreases. Because of the negative gain, after 1 second, it reaches minus 1 volt. When the input becomes negative, the output of the integrator increases, and after 1 second, it reaches again a level of 0 volts. The integrator block is very useful for a variety of applications. One of the most interesting is to be used as part of an analog computer. Analog computers are machines, in this specific case, built with electric components that can be programmed to solve a variety of problems. These types of computers were used to solve problems before the era of digital computers, like the ones we know nowadays. Using op-amps, we can perform additions, subtractions, multiplications by a constant, which is amplification or scaling, and we can also perform integrations. We haven't seen yet how we can multiply two voltages, but we'll see it in a future lesson. In the image, we can see a modern analog computer. This computer is called the analog thing, or DAD. It is comprised by many individual modules that perform integration. It also has adders, multipliers, inverters, etc. The computer is programmed by using cables that connect the different modules, just like a modular synthesizer we saw in a previous lesson. Let's see an example of how we could solve a set of differential equations using this computer. We will start with a set of differential equations that describe a physical system that we want to simulate or solve. It could be a mechanical system, chemical, economic model, or anything that we can model with differential equations. The first step will be to take these equations and identify the different blocks that we need to perform the computation. For example, integrators, adder, inverters, etc. In this case, I selected a group of equations that describe a chaotic oscillator. It is called the Nocé-Hoover oscillator. As you can see, it requires 3 integrators, 2 subtractions, and 2 multiplications. In the diagram, we can see a prototype implementation using block components from the System Modeler library. You can see the 3 integrators. At the input, we need to provide the derivative, and at the output, we will get the integration. For example, the first equation states that the derivative of x is the value of y. We connect the output of integrator 2, which gives the value of y, to the input of the integrator 1. So at the input, we put the derivative of x, and at the output, we get x. We do a similar process for the other equations. To calculate the derivative of y, we need to multiply y times z and subtract x to the result. We take the value of y and z from the integrators and we connect them to the multiplier. The result is connected to a subtractor and we connect the other input to x. For the third equation, we take y and multiply it by itself using the multiplier 2, and we use the subtractor to obtain the operation 1 minus y squared, and that goes into the integrator 3. Let's simulate this model to see the results in System Modeler. As I mentioned, this is a chaotic oscillator, and it produces signals that are not easy to understand the patterns. You can see the values of x, y, and z, and how they change over time. Now let's see how this will be implemented in the analog computer. As you can see in the picture, I use the available blocks like integrators, adders, inverters, and multipliers. Then I connected them using the cables. It is a little bit hard to follow exactly what's going on. But once I had the implementation running, by connecting an oscilloscope, I was able of plotting 2 of the variables and see the nice pattern they make. Implementing the differential equations on the analog computer is sometimes a bit difficult. I made a few mistakes like connecting the wires in the incorrect places, but once the implementation was done, it worked pretty well. We are not going to implement these equations using op-amps because we have not covered yet how to perform a multiplication, but we will implement a simpler differential equation that will give us an interesting insight regarding filters. In the previous lesson, we determined that the differential equation that describes the behavior of the RC circuit is the following. The derivative of the voltage in the capacitor is the difference of the input voltage minus the capacitor voltage and scaled by a factor of 1 over RC. In the diagram, we can see how we could implement this. We only need 2 blocks, a subtractor and an integrator. The integrator has a gain of 1 over RC. The subtractor takes the input signal and subtracts the output of the integrator, which is the value of the voltage in the capacitor, Vc. Using the op-amp circuits we know, we can implement these equations as follows. In this diagram, you can see the integrator circuit we learned in the beginning of this lesson and a subtractor. The subtractor takes the input voltage Vin and the voltage Vc from the output of the integrator. If you look carefully, we are calculating Vc minus Vin, which is not exactly what we need. In fact, it is inverted. We need Vin minus Vc. The reason we calculate it that way is because the integrator is an inverting integrator. In order to compensate the negative gain of the integrator, we provide the negative of the derivative. The gain of the integrator is given by the values of R and C. To implement it, we need to put the same values of RC of the original RC circuit. That's it. This circuit will behave exactly as the RC circuit because we are simulating its differential equation. The problem with this circuit is that it requires more components than just a resistor and a capacitor. We can make a simpler version by using the integrator op-amp to perform the subtraction. Here is a simple implementation. This implementation uses the fact that we can add resistors to the inverting terminal of an op-amp in order to add more inputs. There is an important difference from the previous circuit. In this case, the output of the integrator will be minus Vc instead of plus Vc. In many applications, this may not be a problem, but if we want to obtain plus Vc, we can add an inverting amplifier to fix the design. For now, we are fine getting minus Vc. In this circuit, the input voltage Vin and minus Vc are being added. Then they go into the integrator. In order to match the differential equation, both resistors must have the same value of R, and the capacitor should be the same value as the original RC circuit. This simple circuit behaves as a filter. But why do we add complexity just to get the same result that we were getting with one resistor and one capacitor? Let's compare the RC circuit against this implementation in order to understand the advantages and disadvantages. The RC circuit is what's called a passive circuit. It uses two components and does not require a separate power source to work. That is sometimes an advantage. The filter using an op-amp is an active circuit. The op-amps require voltage to work. The biggest difference is the output impedance. In the passive RC circuit, if we are not careful on what we connect to the capacitor, it may draw too much current and it will affect the behavior of the circuit. The active circuit can provide the output voltage with a low impedance, but the biggest advantage is that we can change the gain of the input voltage if we want. In the previous lesson, we talked about the stability of op-amps. We saw an inverting amplifier in which, by adding a capacitor in the feedback, we could reduce the bandwidth and improve the stability. If you look carefully at the inverting amplifier with a capacitor in the feedback and you compare it with the active RC circuit we just learned, you will see that they are exactly the same circuit but drawn differently. In both, we have a capacitor on the feedback, there is also a resistor in the feedback, and there is another resistor at the input. Let's obtain the actual equations of this circuit. To analyze it, we use the virtual ground concept. The procedure is very similar to the integrator. We have a current flowing through the resistor R1, which is V1 over R1. We have a current flowing through the resistor RF, which is V out over RF. Then we have the current of the capacitor, which is the derivative of the voltage V out times C1. We can rearrange the equation so it looks like the integrator equation. We can see that the gain of the integrator is given by minus 1 over C1 RF. But one interesting thing that we can see is that we can control the gain of the input voltage. The voltage gain will be minus RF over R1. And we can adjust the cutoff frequency of the filter by adjusting the gain of the integrator. The cutoff of a filter is the frequency at which the output is attenuated approximately to 0.7 of the original input, and it controls the bandwidth of the circuit. For example, if we would like to have an inverting amplifier with a gain of 2x and attenuate frequencies above 22 kHz, we can pick a resistor RF of 20K and a resistor R1 of 10K. That will give us a gain of minus 2. Then, with that value of the resistor, we can calculate the capacitor value. In this case, a capacitor of around 361 picofarads will do the job. The frequencies above the audible range will get attenuated and filtered. As a summary for this lesson, we learned how to create an integrator circuit using op-amps. We saw two small examples on how we could use the integrators to simulate or execute a set of differential equations using an analog computer. The analog computer can be either a commercial one, like the DAT computer, or we could create the circuit using op-amps. We also learned how to make a simple filter by using an integrator with feedback. This circuit behaves as the equations of the RC circuit.